All right, next is 10.4. We're going to talk about inscribed angles. So I did say previously that it is very important to know where the vertex of the angle is in reference to the circle. So today, what's the inscribed angles? These are all going to be angles with the vertex on the circle. So we kind of have three different ones. We have on the circle, outside of the circle, and inside of the circle. So those are the three different ones we'll be dealing with. And like I said, today is going to be on the circle. So when you're dealing with an inscribed angle, the vertex is on the circle. And what happens is that the measure of this inscribed angle is half the measure of the intercepted arc. So, okay, let's kind of break that down and go, all right, the inscribed angle. So kind of the word inscribed means that it's inserted into something. It's inscribed in something. So think about when you have like something engraved or inscribed, you're writing on it. So that's why the vertex is going to be on the circle. Now, the inscribed angle. So in this case, it is angle ADB is the inscribed angle because you see that vertex D is right there on the circle. So this is your inscribed angle. Now, the next part of that definition talked about that the measure of that angle there is half the measure of the intercepted arc. So the intercepted arc, that's going to be the arc that's inside the angle. So here, inside of this angle, you can trace from one side of the angle to the other. That's going to be the inscribed arc. So in this case, the inscribed arc for this one is arc AB. So you can now find the measure of the inscribed angle. So there's the angle ADB. You can find the measure of this angle by taking half of the measure of the intercepted arc. So for example, if I told you that this arc is 100 degrees, then that would mean that your inscribed angle then would be 50 degrees. All right, so let's look again. Let's look at this example 1. So find the indicated measure in circle P. So first they want us to find the measure of angle S. So it's helpful if you trace. All right, so here's the measure of angle S. So again, every time you're going to ask yourself, where is the vertex of that angle they're asking you about? Is it on, in, or outside? So let's see. This one happens to be again, and so all we've learned thus far is on. So it's on the circle. So angles that are on the circle, their measure is half of the intercepted arc. So you see the arc in between that angle S is 60 degrees. So if you take half of 60 degrees, you get 30 degrees. So the measure of that angle is 30 degrees. Now you can also use this theorem, it's converse, and the converse is like, okay, well, if we know that the angle is half of the arc, then the length of the arc here must be double the length of the angle. So this arc actually encompasses this angle R, which is 37 degrees. So to go to the outside of the circle, we're going to double it. So we're going to take 37 and we're actually going to times it by 2 because the arc is larger than the angle. We get 74 degrees for the measure of arc RQ. Now in this example 2, you need to find the measure of arc HJ and the measure of angle HGJ. What do you notice about the angle HGJ and HFJ? So find the measure of arc HJ. Well, here's HJ. You can see that it is in between, it is intercepted in between angle F. Well, angle F is 39 degrees. So if we take 39 and times it by 2, that's actually going to give us 78. So the measure of arc HJ is 78 degrees. Now they also wanted us to find, so this is 78 degrees, find the measure of angle HGJ. So if we go from H to G over to J, if we want to find the measure of that angle, it's half of the arc. Well, if you go from the vertex, look what arc it hits. It hits 78 degrees. So an angle that is on the circle is half of the arc. So if we take 78 and we divide it by 2, we get 39 degrees. So the measure of angle HGJ is 39 degrees. Now, what did we notice about those two angles? Well, they're actually congruent. And that leads us basically into, see, this is 78, and so this is 39. That leads us into our next theorem. So if two inscribed angles of a circle share the same arc, then the angles are congruent, just like we found there. So again here, this is inscribed, meaning the vertex is on the circle. If the inscribed angles share the same arc, then the angles are congruent. And you can see that here. Now let's look. These angles, this angle here, this one here, if you trace them, you can see that this is arc AB. Well, if you trace the other angle, here, look what's in between, arc AB. So we have angle ADB, this blue one, is congruent to angle ACB. And another thing you can notice about the letters of these angles that are congruent is that, look, the beginning and the end are AB, the beginning and the end are AB. The only thing that's different is the vertex. So you can see that vertex means they're different angles, however, they're surrounded by the same arc, which makes them congruent. All right, example 3, name two pairs of congruent angles in the figure. So we need one pair and another pair of congruent angles. Remember, congruent angles share the same arc. Well, if you look, we have arc RS. If we go, all right, so arc RS means that the angle is going to start with S, it's going to go to P, and then to R. So we have angle SPR, and we're going to have another angle with the same beginning and end, but just a different vertex. So you can see SQR. Those are two angles that have the same arc in between. Now you can also go the other direction and say, okay, well look, this is an arc PQ. If you go from P to S to Q, so angle PSQ, and you can have the same intercepted arc from PR to Q. So those guys there are congruent angles. All right, so checkpoint, find the indicated measure. We want to find the measure of angle GHJ. Well, where's the vertex? On the circle. So angles that are on the circle, they are half of the measure of the arc. So if you take 100 and divide it by 2, you get 50 degrees for the measure of that angle. Number 2, find the measure of arc CD. I would like you to do this one and then put your numeric answer in the answer blank on the free response question. Now, number 3 is to find the measure of angle RTS. Well, let's see. We have R to T to S here. Well, the vertex is on the circle. If the vertex is on the circle, that means it's half of the intercepted arc. Well, the intercepted arc here is RS. Well, this angle here has the same exact intercepted arc. So angles that share an arc are congruent. So the measure of this angle is also 31 degrees. Now, we can also have triangles and polygons that are inscribed inside of a circle, and it only works in some cases. Now, with a right triangle, this only works when the hypotenuse is the diameter. So if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. All right, well, conversely, remember we can flip that around. That's what converse means. If one side of an inscribed triangle is a diameter of a circle, then the triangle is a right triangle and the angle opposite the diameter is the right angle. So basically what that's saying is if you know, like right here, if you know AC is the diameter, in which we do because it's going through the center. So we know AC is the diameter. So since AC is known to be the diameter, then it is okay for us to conclude that this is indeed a 90-degree angle right there. Now, if we had a picture like this, A, C, and B, and we had this to be 90 degrees, if that angle is 90 degrees, then we can conclude that this is indeed the diameter. So we're allowed to say that this is the diameter if the 90-degree angle is there. And if the diameter is there, then we're allowed to conclude that that's a 90-degree angle. So that's kind of how that works. So the measure of angle ABC is 90 degrees if and only if AC is a diameter. Now, for the polygons, a quadrilateral is a polygon, so four-sided figure, can be inscribed in a circle if and only if its opposite angles are, and I know you're going to remember this word, supplementary. So the only way that you can fit a quadrilateral inside of a circle is if the opposite angles are supplementary. So basically, the only way you can put a circle around this quadrilateral is if you know that the measure here of D plus F is equal to 180 and that the measure of E plus G is equal to 180. Because remember, inside of every quadrilateral is 360 degrees. So here you're going to be adding the opposite angles to make sure they add up to 180. So with that being said, we can do example 4 and find the value of each variable. Well, since it is a quadrilateral inside of a circle, we know that the opposite angles are supplementary. So here are opposite angles. They both are x. Well, I know the definition of supplementary means two angles whose sum is 180 degrees, and that's the equation I just made. Two angles whose sum is 180, and now you can solve. So 12x is equal to 180. If you divide by 12, that's going to give you 15. Now we also have y's there in the quadrilateral, so the y's are opposite of one another. So opposite angles in a quadrilateral inside of a circle are supplementary. Supplementary are two angles whose sum is 180. So you go through, combine your like terms, divide, y is 20. Very good. All right, in B, all right, so we're going to solve for each variable. Well, opposite angles are supplementary. Well, that's two angles whose sum is 180. Make the equation, solve, so y is 80. Very good. I would like you to go ahead on your own and solve for x and put your answer in the question in the video. Thank you.